speakers today are pretty awesome. I had a chance to talk to them for a while. They have pretty long intros, so I'm going to try to do it justice. So speaker number 1, Mr. Amol. He is a product marketing director at Cadence. Since joining in 2018 as a senior product manager, he led the development of many successful hardware and software products, including Tensilica's latest Vision P1 DSP. Yes. I'm trying to think. Man, there's probably like real substantial stuff I should say about him, but I'm sure he'll give you a quick intro as well. And then our second speaker is Vencatesh. And Vencatesh has more than 15 years of experience in DSPs and automotive and consumer radar signal processing, with some 4G and 5G communication signal processing at the edge. So you kind of get the sense we're about to talk about some radars. And I'm going to go away now and start a timer. And while I'm doing that, they'll just say some words to you. And let's get started.
Well, thank you, Mo. So, yeah. Welcome, everybody. I know this is the second last session, so we'll try to make it fun and interesting. So I'm Amol Borkar. I'm the Director of Product Management and Marketing. I'm part of the Tensilica Products Group at Cadence. And along with me is Venkatesh. He is our in-house radar, LiDAR, communications expert. He's very, very smart, really. So all the tough questions, please ask him. I'm just from the marketing side. So the overview for today's talk is we're going to go over uses of radars, what are the basics, radar signal processing, advancements, and of using AI in here. So when we were putting this talk together, Jeff told me specifically, we want to make this a interesting technical talk, but it doesn't have to be like a PhD dissertation. We're not going to get into equations and all of that. So it should be more focused on, provide you enough technical information about the radar processing chain, what are the common terminologies, how some of the blocks work together, and then that way you have an idea of the end-to-end implementation of a radar system. So when you're talking to your engineering colleagues, you at least can challenge them if you don't understand something, you have that level of knowledge. So with that, let's get started. So let's take a look quickly at some of the uses of radars, the various different types of sensors that are typically used in radar systems. So I think the slides are moving. Oh. So I think most of us are familiar with radar systems which are used in weather monitoring, typical mil-aero applications, and then also our favorite police using the speed guns to find out how fast we were going. But that's when radars were quite large and very, very expensive, obviously. They have come down to a better price point, so now we're starting to see different types of usages of radars. Obviously, a lot of usages of radars in the ADAS or the automotive space. We're seeing them in drones. We're seeing them also in some of these IoT, gesture-related applications. And many more usages are coming as the price of radar sensors is reducing. So in terms of sensors, I think many of us are quite familiar with a whole bunch of sensors over here. Like, we've got cameras, radars, LiDARs, ultrasonics, and each of them have their pluses and minuses, right? Like cameras are good for object classification, but in some cases, maybe they have limitations operating at night if you can't see things very well. Obviously, as many of us know, using a camera in a car when it's raining at night, it's almost impossible to see the road. So in those cases, maybe having a combination of a variety of sensors like LiDAR plus radar plus camera will give you a very, very large spider chart covering nearly all aspects, making it a sort of like a unified solution to cover most of the applications that you're targeting. Now, the basics of a radar, I'm sure most of you are familiar with this, but we'll still go over it over here, is your transmitter basically fires a signal. It goes to an object. A lot of it scatters, but some of it comes back. And then using a different number of calculation techniques, you can figure out how far that particular object is from your emitter or your transmitter. So this is where the functions of radar and different types of classification comes up. So The idea with the radar helps you to understand how far the target is from the particular antennas that is firing the signal. You can also determine velocity, how fast the object is moving with respect to the radar. And then, in a lot of cases, also angle of arrival. Angle of arrival, or AOA, some other terms you might have heard of also is DOA, which is direction of arrival, or beamforming. This is essentially knowing relative to the radar, where is this particular object. And obviously, there's different levels of categorization. Some of these radars can just do maybe range, or some can do velocity, and some can do all of the above, or even more. But this is where, using a particular modality of the radar, which is a FMCW, or frequency modulated continuous wave radar, can be used to do three-dimensional measurements of the object, or even in some cases, 4 dimensions. And I will explain what those are. So, in that regard, the FMCW radar system, if you have a 3D radar system, it can do the determination of your range, as we mentioned, how far is the object, how fast it's moving, and then also it's the angle of arrival, or the beamform, or the direction. So this basically allows, depending on the classification of the radar, if it's a short range, it's a long range, or ultra long range, you can have different levels of ranging, of signal detection, let's put it that way, or object detection. So on the top, we have our traditional 3D radar, which can do your range, and your Doppler, which is your speed, and azimuth, which is your angle of arrival. But at the bottom, we have what are the 4D radars, the newer radars. This can do the 4th dimension, which is called elevation, which is depending on how high that particular object is with respect to the radar. So that gives you your 4th dimension. So how do we come up with this data cube, like in terms of once you want to start processing and figuring out where these objects are in the environment? We have to create, essentially, I'm sure you've heard of this term, the radar data cube. And we'll walk through how we actually come up with this. So you have your antenna, which can basically fire out a chirp, and then you receive the chirp back from the object that it's reflected from. You do some correlation or autocorrelation between the transmitted signal and the receiving signal. This can be done on the different antennas that you have. Usually you have multiple antennas on your array. You repeat this for n number of chirps. Again, it's an oversimplified example, but with this coherent processing interval, or CPI, you can put together this data cube. So you can see over here, you have your antenna channels, and then you have your slow time, and then you have your fast time for your data cube. This usually forms like a 3-dimensional data cube that is then further sliced to figure out where your objects are, how fast they're moving, the AOA, and the elevation as well. So in typical automotive systems, you would use 77 gigahertz or in that range of wavelength radar signals or pulses to find your various objects. Obviously, depending on the use case, you can have lower gigahertz or higher gigahertz as well. So the types of FMCW radars very much depends on the number of antennas you have. So in some cases, you could have just one single antenna that's firing a signal, but then you can have multiple antennas receiving. So this could be SIMO, single input, multiple output, or you could do it the other way around also, where you have multiple inputs as well as multiple outputs, most commonly known as MIMO. And then how you want to do the multiplexing, once you get this, when you transmit your signal, you can do in most commonly 3 different fashions. You can do TDM, which is time division multiplexing, frequency division multiplexing, or even Doppler division multiplexing. Now, we don't have time to go into all of them. We're going to be focusing on just the MIMO, which is the multi-input, multi-output. But the advantage of multiple inputs and multiple output is you can get higher angular resolution with the use of all these antennas. Because typically in a MIMO system, let's take, for example, you have 8 transmission and 8 receiving antennas. You can get a really high resolution of a data cube because you can generate basically 64 virtual channels with this antenna array. Now to go deeper into the radar signal processing, I'm going to hand it over to my colleague Vencatesh.
Thank you, Amol. So we saw the data cube in the previous slide. that Amol spoke about. So this slide is going to talk about the signal processing on that data cube to detect a target and its properties that Amol just spoke about. That's the range, velocity, and angle. So the typical radar signal processing chain for a 4D imaging radar in particular, which is shown here, starts with computing the range Doppler FFTs, which are shown right on top. Here, you find the target's distance and velocity using FFTs. This is followed by typically a data integration module and a CFAR module after that. Once you detect some targets, you may want to do a MIMO demapping. This MIMO demapping typically comes in case of a 4D radar. Also, one may optionally do velocity compensation. This could be followed by an optional beamformer module and some angle of arrival computation to find the azimuth and elevation properties of the radar. This is then followed by some modules like pruning, point cloud generation, clustering, and target tracking. All these modules could be considered as post-processing or some form of back-end signal processing. So we'll look at each of these modules a little bit in depth in the next set of slides. So let's start off with the first module. That's the range Doppler FFT. So the range Doppler FFT, as the name gives it away, it helps to determine the target's distance and velocity using a time-to-frequency transform, also referred to as fast Fourier transforms or FFTs. Here is an example of the range Doppler FFT performance on the data cube. So once we get the signal into the baseband domain, which is the IF signal shown here in the form of a data cube, you perform the first FFT transform, also referred as to the range FFT, to determine the position of the target. This is followed by a second FFT transform, both put together, the second FFT transform being called the Doppler FFT. Both these transforms put together help to find the target's position in the range axis and the velocity. Besides FFTs, these could also involve operations like windowing, which could help do some spectral filtering, and also some sort of scaling of data. The scaling typically comes in case of fixed point processing, domain signal processing. A 4D imaging radar typically has a large number of FFTs to be computed, which implies that your compute platform should have really good capabilities to handle that. The next module is the data integration module. So this is a step where the FFT data is pre-processed before passing on to the CFAR. It does, basically, integration of the signal across the various antennas with or without phase compensation. This with or without phase compensation is also called as coherent or non-coherent integration. Here is an example of a non-coherent integration operation where the FFT data, a magnitude is computed on the FFT data of the range Doppler data cube and then summed across to generate a range Doppler response map, as shown here. So besides magnitude computation that I spoke about, you could also have some form of phase corrections, you could have FFTs, you could have log computation also getting involved in this. I do not want to go into the technical details, so I've kept it as terminologies over here. The next module in the signal processing chain that we saw was the CFAR, or the constant false alarm rate kernel. So the constant false alarm rate kernel objective is primarily to find the crude presence of the target in the scene. So it does so by using a 1D, 2D, or 3D computation. It uses a sliding window filter, which can do averaging or sorting to determine a threshold, which is used to find local peaks in the environment. Here's a diagram that shows the CFAR algorithm in a lot more detail. So the next one that we found, the range and Doppler, we try to find the angular position of the target. So the angular position of the target is basically, or the angle of arrival is basically used to find the spatial position of the target in the azimuth and elevation direction. And here is an example that shows how this is done. So we spoke about multiple transmitters, multiple receivers. So we are just going to focus on the receiver side over here. So a copy of the signal is received back by all these receiver antennas. So let's say for a range Doppler position, shown on the blue dot over there, you see that there is some difference in the phasors, which are shown in those circles with arrows. There's some difference. So can we leverage this to do the angular position computation? Yes. So you could use algorithms like FFTs, root music, or beam scanning to do this. So here is a reference example of a beam scanning algorithm that is used to find the cyclist and the position of the car. Also, the figure on the right shows the FFT-based method that's applied to those phasors to find the position of the target. The next module that I'm talking here is the clustering algorithm. The clustering algorithm primarily came from databases and those kind of domain spaces. But here it is used to group detections that are possibly arising from a single target. So there could be multiple reflections that could be coming out from a radar from a single target. So the algorithms typically used are dbScan, k-means, or some custom algorithms that people like to design. But if you open it up and try to see what does it involve internally, it generally involves operations of data sorting, data gathering, comparison, data reordering, etc. So a multi-object target tracker is what we would be talking over here in this slide. So the objective of the multi-object target tracker is to find the position of the target in future frames, associating data across frames, and managing some track history. So here's an example of two targets that have moved up a certain path as shown by track 1 and track 2 over time. In the current frame, there are certain observations that have been generated by the radar head. So now the problem arises, how do we associate these observations with the tracks? So the process is, we start off by using some form of a prediction algorithm that can predict where the target could have possibly moved. So this is done by algorithms, classical algorithms like Kalman filters, EKFs, UKFs, etc. So the red boxes show the predicted position. So the second step is, now that you have the measurements, why don't you try to gate those measurements around these predictions? So for this, you try to use algorithms like Mahalanobis distance, GNNs, etc. Once the measurements are gated, you will try to associate those gated measurements with those predicted tracks. Once the data has been associated using algorithms like GNN, PDAF, JPDAF, MHTs, etc., you would want to update your prediction. All of this typically has a lot of complex linear algebra that lies underneath. They could be doing complex matrix decompositions, matrix inversions, a lot of math going behind, and a lot of matrix ops going behind it. Now that we have seen the blocks of a classical signal processing, let's move on to something that's nice and interesting and is catching steam in the market, which is applying radar AI to radar data. So we all know that AI started getting applied first on vision sensors and then on audio data. Since 2020, we see that both the academia and industry has started gaining interest in applying AI to radar data too. The challenge till this point of time frame was that there was no much labeled data sets available in the radar subspace. But since 2020, a lot of data sets have started appearing in the public domain, and more researchers have started getting interested in this, as this is the next big thing. So radar AI engineers basically have started trying to solve two sets of problems. The first one being classical signal processing problems, like what we saw in the previous slides, to achieve some better accuracy than traditional methods, or try to see that if you could get more information than those 3 parameters that we talked about. So they're trying to apply vision-like problems on radar data to do segmentation, classification, etc. So I spoke about radar data sets being available in the public domain. So a few of them have various representations. One, a popular one, is a point cloud-based data set. You could sometimes have data sets that actually give you the raw ADC data also. There are some that do an FFT and provide those data as RAD cubes, RA cubes, or RD tensors, or you could have spectrograms. So we see that the AI engineers on radar are trying to solve various sets of problems, like classical problems, as I spoke about, that is trying to replace the tracking that we saw previously with AI, trying to do some detections using AI, or trying to find the angular position of the target using AI. Newer areas like classification and segmentation, microdoppler-based gesture recognitions or multi-class segmentations are something that are being applied. And there are newer areas that are not vision-centric, but are like finding the ghost targets. Ghosts are a big problem in radar. So you want to solve that using AI, or you want to do some sort of interference suppression. So these are new interesting areas that people have started digging deep and, again, should catch someone's interest. So with this, I'll hand it over back to my colleague, Amol, to present the rest of the part.
Yeah. Thank you, Venkatesh. So just to wrap things up, I think we gave you a fairly high-level overview of how radars are used, how you come up with the general data cubes that are being processed, comparison between a variety of sensors. We also introduced some of the basics of the FMCW radar, and then we were going through, in some level of detail, the RSP, the radar signal processing chain, and the various steps, and provided some details of what those blocks actually do. And as we know, this is 2025. AI is coming everywhere. We're starting to see AI also proliferate in the radar space. And there have been a good number of advancements actually over there. But we're going to start seeing probably a heavier hand of AI. And then there's going to probably be a combination of classical signal processing with AI to take on the next level of challenges that the current radar systems can't solve. So with that, I'd like to thank you all for your time and open the floor to some questions. Thank you to our hype man over here.
Yes. Any questions? Do you have questions? I'm supposed to ask one that I have prepared, but I want to see if somebody has one.
Oh, there's the first one.
Beautiful. Yeah. Why not?
How would this pipeline differ if you're doing something that's like millimeter wave or ground penetrating or those kind of radars that are can be below the surface?
Yeah, so it would be more or less the same. The principles are going to remain the same. There could be a different set of algorithms that could be applied. We didn't go into the details about every algorithm, but there are some specialized forms of FFTs, you could say, for ground penetrating radars that people may want to use. There could be a different form of filters that people may want to use on the signal before processing it. But more or less, the principles remain the same.
Can you talk a little bit about fusion, meaning using radar with other modalities? I think you talked about it earlier in the presentation.
Sure. Yeah. Want to take that?
You go ahead.
Okay. So yes, radars, as we saw in the previous slide, do not have all the capabilities, and it's not one God sensor for sure. So sensor fusion is a mandate. There are going to be almost for certain fusion between cameras and radar sensors that are going to happen at least in the automotive space. It's needed because each one have some complementary skill sets. Now, there are approaches where people are doing it in the classical signal processing domain also. There are people who are doing it even in the AI subspace. So people can do it with various form factors, like some people like to do early fusion of signals, some people like to do mid fusion, some people like to do late fusion. So these are topics of their own for a separate discussion. But yeah, there's an equally interest in this subspace.
You stole my thunder about the mid and late fusion. I was going to add that part.
Sure.
Yeah.
So I have a question for the classification. Are you able to classify on the vehicles like the car, sedan, 18-wheeler, or truck, pickup, a van, something like that?
Yeah. So there are interesting papers that are available in the domain space. I mean, these are all public information where people are actually applying a lot of AI to radar signals to classify the size of the object or the size of the vehicle on the roads. In fact, there's one deployed on some of the Indian highways where it's actually doing speed monitoring per vehicle basis. So they're using the similar technology over there.
Okay, the next question. In your radar design, how many objects you can track and detects at the same time?
Sure. So we are not talking about a specific product over here. So probably you want to introduce the organization. I'm not sure.
No, Jeff said this is a technical talk, so I'm not supposed to promote our products over here, unfortunately.
Okay.
But as you said, on the technical aspect, there's no real limitation. The only thing we can say from the product side of things is, however you want to run the algorithm, whether it's early fusion, late fusion, mid fusion, it's a mix of classical versus AI. Our IP portfolio supports that. Again, the number of objects, the size of the objects, the latency or the frequency you want to do, all determined by the size of the data cube coming in, how much processing is needed, and that, just as you know, for almost everything, varies depending on your input parameters, right?
Yeah, okay. Then the next question: how far you can see the object?
Yeah. So probably we can talk about this offline because we are not doing any specific thing.
Yeah.
We are just presenting a general solution here. And these depend on the number of antennas that you have, the parameters that we spoke about, like the chirp bandwidth and things like that.
Yeah. Also probably the frequency of the antennas, all that stuff
comes into play.
Yeah.
So when you apply this technology to, let's say, the automotive space, your device is not the only transmitter in the environment. Just about every car has radar these days. So how do you deal with that interference?
Perfect question. So radars have this big problem of having very strong interference from nearby objects. So people apply different techniques on top of it. So you could apply some sort of signature on your transmitted waveform, and you could match it back again once you receive the signal while you're doing your range processing. So there are techniques wherein you may want to scramble it with some signature, like a PN sequence. There are people who actually apply different phase factors per radar. So you could have a signature which will determine a phase factor that will change the phase of these waveforms that we are transmitting. And that will help make it a little bit agnostic. So if you go back, these are something like that have been applied in the CDMA space of the communication, if you're aware about it. And then there are some techniques that went on from the CDMA to when you went to the 4G domain space. So these are all techniques that are starting to get applied onto the radar also. So, yeah.
Thanks.
Yes.
Hello. You mentioned ADC data sets on your slide. Do you have any kind of sites that would form like any kind of data sets with respect to pulse Doppler?
GitHub?
Data sets for ADC?
Yeah, so there are multiple GitHub links which have these data sets available for you.
Okay.
It's just about searching it. It's all public knowledge.
Okay. All right. Okay.
Yes.
Tesla is going to launch the Cybercab testing in Austin in this June. So what's your comment on the two directions, Waymo's LiDAR's solutions and the Tesla's camera-based? What's your prediction or comments on the two directions? Which will be the winner?
I think that's controversial, but I don't want to answer that over here. I don't know.
Yeah, okay.
From the business side, I can say one thing, but...
Sure. Okay. So each of these sensors have their own capabilities, right? People have tried to prove with various modalities that things are pretty safe. We cannot claim that only a camera-based solution would be better off than an only radar-based solution. We think that people will have to figure out what modality best works for them. So they would have to try it out and see what best suits them.
Yeah. And just to add to this point, I think, aside from just going on one sensor on another, I think many of us have seen some of the videos also of the tests where they try to simulate kids crossing and all of that. And we know, I think we all also know if we just operate purely with cameras, we ourselves have difficulty seeing at night when it's raining and there's poor visibility. So augmenting that with, with other sensors, as I think we pointed out, that probably gives you a wide coverage for all the scenarios, but can't stop anybody from doing what they want and claim what they want. So,
Just give me the last question, please.
So I have a two-part question. So I'm trying to understand, what is it, how to make radars easy to use in industry, right? So there are two parts to it. One is cost. Cameras have been so cost-effective. They cost so less, but there is a lot of computational load on top of it, right? So how do you think like radar in what generation or like how they are approaching right now? And again, I see a lot of range, right? It's long distance range, but I think the industry, what they want is short range, more precision, more accuracy. So what's your take on it, and where do you think this industry is heading with? I know, like, I see that AI can be used, but again, measurement is something you need deterministic, right? You can't just use AI for all of it and make sure it works, because in a deterministic world where you need accuracy, I don't think the computation doesn't work with it, right?
Okay. Do you want to answer?
You go first.
Okay. So coming back to your question on, sorry, sorry about that. Could you just repeat your first question? Sorry about that. Yeah.
So what I want to understand is it's basically camera versus radar or any other system, right? So first is cost.
Cost. Okay. So thanks for the keyword. So the cost of radars are definitely expensive than a camera, right? We know that there are vehicles running on the road today with somewhat semi-automatic driving with just a 2-megapixel camera on it. We know our phones have much more megapixels than the cameras on those systems. But the radars are not going to be as cost-effective as a camera sensor for sure. But it's not going to be as expensive as a LiDAR. But people are trying to get down the cost of both these sensors, both LiDARs and radars. They're trying to get it down. I think it's about volume when prices start coming down. Both of them need good amount of compute capabilities. It's not as simple as camera systems to do. You need a lot more compute capabilities on your systems to solve radar or LiDAR data.
Please, everybody, give it a big round of applause for our speakers. It was awesome.